Good day, friends. Today I want to teach a simple harmonic motion, as you can see on the board. What is simple harmonic motion? Simple harmonic motion is the motion of an object whose acceleration is always directed towards the center, and it is proportional to its displacement from it. Simple harmonic motion, once again, is the motion of an object whose acceleration is always directed towards the center, and it is proportional. That is to say, the acceleration is also proportional to its displacement from it, meaning the acceleration of a body undergoing simple harmonic motion will be proportional to the displacement of the same body from where? From the center. Then the acceleration must always be directed towards where? Towards the center. So meaning, while acceleration is towards the center, displacement is away from the center. So acceleration and displacement are directly opposite each other. Acceleration and displacement are directly opposite each other. And for that, mathematically, that definition can be expressed as A proportional to minus X. This is direct proportionality, where A is acceleration and X is what? The displacement from the center or from the equilibrium position. Now, why is this minus there? That minus is there because acceleration and displacement are directly opposite each other. Because while acceleration is towards the center, displacement is away from the center. And then later, I'm going to prove to you later that A is going to be equal to minus omega square x, where omega is the angular speed of the body undergoing simple harmonic motion. So let me give you the diagrammatic illustration. This is it. This is a simple, this is a rotor stand, a rigid support. Then if you have a thread, this one is a thread, and a bulb is attached to the thread. That's to the thread. This is a pendulum bulb. Now, this place is the center, which I also refer to as the equilibrium position. Equilibrium position. Some also call it mean position. Some also call it mean position. So it has three different names. So you can see, this is it. This is the rotor stand, while this is the pendulum bulb. So a swinging pendulum bulb is a very good example of a body undergoing simple harmonic motion. So that if here is the equilibrium position or the center now. Can you see? Here, where my hand is right now, is the equilibrium position. So if I displace it this way and I release it, so it begins to move to and what? And fro. Now, as this bulb is moving, acceleration is directed towards where? The center. That's towards here. Towards here. While you can see that displacement is how? Is away from where? From the center. The displacement is away towards this direction, to my left hand side. While acceleration is to the what? To the right hand side. So examples of bodies undergoing simple harmonic motion, we have a swinging pendulum bulb. Please don't just, if you are asked to give an example, don't just say pendulum bulb. So if you say pendulum bulb without telling us that it is swinging or it's being displaced and released, you are going to be wrong. So it has to be in what? In motion. So we displace the pendulum bulb this way to point A, and then we release it to swing about, to move about the equilibrium position. So it will move about the equilibrium position, it will move to what? To point B. So this is the path of the motion of this object. So it moves from A to B, then also through from B back to what? To A. So from A to B is half oscillation, while from B to A is also half oscillation. Then a complete oscillation is from A to B and then back from B to what? To A. Okay? So we call it C, the center, we call it C. Alright. So other examples of bodies undergoing simple harmonic motion, I believe you know them. Can you mention them? Okay, we have a vibrating tuning fork. We have the beating of the heart, the motion of the piston of a gasoline engine. What again? We also have a loaded test tube slightly displaced in water. They also have a loaded spiral spring that is slightly displaced and allowed to oscillate vertically. So these are good examples of bodies undergoing simple harmonic motion. Then we move further. There are terms, very important terms, that are used in simple harmonic motion. Terms in simple harmonic motion. Number one of such terms is what I call amplitude. Amplitude. What is amplitude? Amplitude can be defined as the amplitude of a body undergoing simple harmonic motion. It can be defined as the maximum displacement from the equilibrium position. From the equilibrium position. Okay, the maximum displacement from the equilibrium position, and it is denoted by what? By A, capital letter A, and measured. So denoted by A and measured. It is measured in what? In meters. Meaning amplitude is a distance. That's what it means. So it is a distance that can be measured. So maximum displacement of a body undergoing simple harmonic motion from the equilibrium what? Position, or from the center, or from the mean position. Then number 2 term is frequency. What is frequency? I will not have that time to write everything on the board. Frequency can be defined as the number of oscillations completed in what? In 1 second. The number of oscillations completed in 1 second. That is what frequency is. Frequency of oscillation. And it is denoted by what? By F, and measured in what? I believe you know it, hertz. So it's measured in hertz, which is Hz, hertz. That's the unit for frequency. And for your information, frequency is the reciprocal of period. F is equal to 1/T. Then number 3 term is period. What is period? Period can be defined as the time taken for a body undergoing simple harmonic motion to complete one oscillation. That's a to and fro motion. Time taken to complete one oscillation, and it is denoted by what? By T, and measured. Period is measured in seconds. So even if you are given a minute, you have to convert to what? To seconds. Okay. Then you can also write that T is equal to 1/F. So as frequency is the reciprocal of period, period also can be expressed as the reciprocal of a frequency. Okay? Then another very important term, which is number 4, is what I call the angular speed. Although angular speed and angular velocity here, they are being used interchangeably. So, and what is angular speed? That is the angular distance turned through over what? Over the time taken. Or angular velocity can be defined as the angular displacement by what? Per time. Over the time taken. And it is denoted by what? By omega. This is not W. That's what? Omega. It's a Greek letter. And it is measured in radians per seconds. Radians per seconds. For example, if this is a rigid support, as you can see on the board, then you have your bulb here, then you now displace this bulb. You displace this bulb from here to here. So you have to draw the same line this way. So this is the part taken by the bulb. Now this is the angle turned through. This angle what? Angle theta that is being turned through by the object. So angular velocity omega is now going to be equal to what? Angular displacement over what? Over time. Please take note of this equation. We are going to be making use of these equations very soon. So that if I make theta the solid formula, theta is now going to be equal to omega what? Omega t. Jot this equation somewhere, so please don't forget. Even we still have some other formulas for angular speed. There's another formula that says omega is equal to 2 pi f. Omega is 2 pi f, where f is the frequency. And please don't forget, the unit of angular speed is radians per what? Per second. Then this one can also be expressed as omega equals 2 pi times what? Times 1 over t. Since f is equal to 1 over t, then omega will now be equal to 2 pi over what? Over t. Okay, so this is the expression for angular speed or angular velocity, because I told you they can be used interchangeably. Then the last one, the last term I'll be giving us is the linear speed. So what is linear speed? At least you know what speed is. Distance over what? Over time. The distance traveled, covered by the body undergoing simple harmonic motion divided by the total time taken. While linear velocity is going to be displacement over what? Over time. So, and the symbol is V. And V is going to be equal to distance over what? Over time. S is standing for distance, while T is standing for time. And the unit for speed is meter per seconds. Meter per seconds. Alright. Now, I want to go into the relationship between the speed of a body undergoing harmonic motion, that's linear speed, and angular speed. But before I do that, I think I need to ask a small question. Now, example. Example number 1 now. Looking at this diagram, so let's brainstorm together. Looking at this diagram, you have a bulb here at equilibrium position and it's being displaced to point A. Being displaced to point A and then released and allowed to oscillate. So it moves about C and then comes to B. So this is the part of the bulb. Now, assuming the time taken, assuming the time taken for the bulb to move from A to C is 1.0 seconds. Or let me change it to 0.25 seconds. So who can tell me what is the period of oscillation? Time taken to move from where? From A to C. You know, you release it at A and then it moves to what? To C. So who can tell me what is going to be the period of oscillation? Now please don't rush. For you to solve a problem like this, you must define what period is. What is period? The time taken to what? To complete one oscillation, or time taken for one complete oscillation. Now, you must also define what a complete oscillation is. A complete oscillation, please, for your information, is not from A to what? To C. I told you the other time that half of our oscillation is from A to what? To B. Or from B to what? To A. That's half oscillation. A complete oscillation has to be from A to B, then back from B to what? To A. From A to B is only two. Is that you are going on a journey and you are coming back. You have only gone. If you move from A to B, you have only traveled. You've only gone from home. You've gone away from home. Then you have to be back from where? From the journey, for a journey to be complete. So from B to A now, back to A, that's you have come back from your journey, so you've completed your journey. So from A to B is half, and from B to A is what? Is also half. So from A to B, then back from B to A makes a complete oxidation. So what do we now think from A to C is going to be? So from A to C will now be 1/4 of what? Of complete oscillation. I believe you understand what I mean. Reason because if from A to B is complete is half oscillation, so A to C is half of that, of half of what? A to B. So half of half, that's what? 1/what? 1/4. If you take half of half, that's 1/4. Okay, it means 1/4 oscillation takes how many seconds? 0.25 seconds. So what is one complete oscillation? What is that taken out for one complete oscillation? Because that's our period. So 1/4 oscillation, I'm already solving, please. Oscillation takes what? 0.25 seconds. So one oscillation is now going to take x seconds, unknown x seconds, and I want to do it like direct proportion, so that if you cross multiply, if you are familiar with stoichiometry in chemistry, we use direct proportion, because the number of oscillation is going to be direct proportional to the time that is going to be spent. So if you cross multiply, it means x/4, that's x times 1/4, will be equal to what? 0.25. Then find x. X is going to be equal to 4 times what? 0.25. That's what? That's 0. Is it? No. 1 point what? 1.0 seconds. So the answer is 1.0 seconds. So if you say therefore period T is 1.0 seconds. Period T is 1.0 seconds. So from there I think we can move on. We go to the relationship between linear speed and angular speed. Relationship between linear speed and angular speed. That's V equals to omega r. I want to show you how they arrive at this. Where your linear speed is V and your angular speed is omega, and r stands for the amplitude. Some they express it as V equals equals to omega A. Omega A. Now, how do we start from? Did you remember the diagram I drew for you? A body here, then displace here. No, this a rigid support. You displace it to this place so that it has turned through angle what? Angle theta. Then it must have traveled distance what? S. From here to here, distance S. Are you following? Then I said angular speed is equal to the angular distance traveled over time, and then theta is now going to be equal to omega t. So I can call this one equation what? Equation 1. Please just follow me. Now this is the distance traveled, which is also which can also be called length of arc. If you are familiar with measuration in mathematics, measuration of plane shapes, length of arc. And if you can remember, what is the formula for calculating length of arc? Then please don't forget that from here to here is your what? Is your amplitude, which is the radius. Is how you call it A or what? Or R. From here to here and from here to here is the same thing. A equals to R. Okay. So what is the formula for calculating length of arc? So I want to calculate what this S stands for, because this is the distance traveled by the body undergoing simple harmonic motion. Remember, length of arc is what? Formula for length of arc? Theta over what? Over 360 times what? Times 2 pi r. But we are using pi what? Pi radian. And pi radian is equal to 1 what? 80 degrees. This pi is a radian, please. And pi radian, if you are conversant with your trade in further mathematics, pi radian is 180 degrees. The equivalence of pi radian in degree is 180. Such that 2 pi radians now will not be equal to what in degree? 360 degrees. So let's go back to this equation. Now, what's our length of arc? Length of arc, which is S now. You know, I said S is our length of arc. Will now be equal to theta over 360 times 2 pi r, and S will now be equal to theta over 360 times now 2 pi. 2 pi is what now? 360 degrees. So I'm going to have 360 times what now? Times this and r, and this one will cancel this, so that distance will now be equal to theta what? Theta r. You can see. Can you see? Okay. So please, I want to do something here. Theta is equal to what here? Omega t. Please also make theta the solid formula here. Here, theta is going to be equal to what? S over what? Over r, divided by S. Let me call this one equation 2. Okay? Equation 2. Then don't forget again that linear speed. What's our linear speed? V is equal to distance. Distance is what? Distance traveled. That's what? We use S over what? Over time what? Time t, meaning V equals S over what? Over t. V is equal to S over t. Okay. Now, what is our S here? S is what? Theta what? R. There's S here, isn't it? Okay. Then what do we have here again? We have theta here. Okay, there's t here. Okay, this I think here we have to make t the solid of what? Of formula. Please look here. We want to substitute on some values from this equation and this equation here. What is t here? I want everything to disappear. The only thing I'm looking for is V, omega, and what? And my amplitude. And don't forget, I've said that my amplitude can be what? R or what? Or A. Please don't ever forget that. So please, let's come back here. I want T to disappear. I want S what? To disappear. So S is here already. So let's make T the solid of what? Or formula. T here will now be equal to what? Theta over what? Over omega. Please take note of this. So these are the two things we are using. Not even equation 1 and 2. So V will now be equal to what? We are substitute. What is your S? S is what? Theta what? Theta r. Then over, what is your T? Theta over what? Over omega, okay? So we are getting there. So from there, V, we now equal to theta r divided by what? Theta over omega. And then V will now be equal to theta r times what? Change this on to multiplication. That's going to be omega over what? Over theta. Theta cancels what? Theta. So V will now be equal to r times omega, and if you rearrange, this is going to be what? Omega what? Omega r. This is a very important formula, or you say V equals to omega A. So this is the formula. This is the relationship between linear speed and angular speed. Meaning linear speed is equal to the product of angular speed and what? And the amplitude of oscillation. Then please don't forget again that linear speed is measured in meter per second. Angular speed is measured in radian per second, while amplitude is measured in what? In meters. Okay. So from here, I think we can solve another problem, another example. Let's solve another example. Example. Find the angular speed of a body undergoing simple harmonic motion with a speed of 10, let me use 2 meters per second, and an amplitude of let's say 0.5, or let me use 0.8 meter. It's a very simple question. Solution. Very simple question. Find the angular speed of a body undergoing simple harmonic motion with a speed of 2 meters per second. So they didn't even need to tell you that this one is linear speed. Once you see the unit, and then amplitude of 0.8 meter. So we have linear speed. Let's interpret our problem. V is 2 meters per second, while amplitude A is equal to 0.8 meter. Just apply the formula I gave now. V equals what? Omega what? R. And omega is what we are looking for. So substitute your values. 2 will be equal to omega times what? 0.8. And therefore, omega is equal to 2 over 0.8. That's what? 2 divided by 0.8. What do we have there? 2.5 radian per second. This formula is also very useful in circular motion. Very useful in circular motion. Okay. Now, from here, it can also be shown. It can also be shown that the linear speed, please you can judge, you can write that down. The linear speed of a body undergoing simple harmonic motion at every point in time is given by V equals to omega root A square minus S square. This is speed, this is angular speed, this amplitude, why this what? Displacement in meter. Amplitude in meter, angular speed in radian per second, and then speed in meter per what? Per second. It can be shown. And how? It can be explained from a circle. Let me explain that from this circle. Simple harmonic motion simply can be explained from from a circle. Just watch. This is it. Can you see? Now, draw a vertical line and another line which is horizontal. So here is the center of the circle. Call that place C, which is the center of oscillation. The center of the circle is the center of oscillation, which is also known as the equilibrium position or the mean position. Then I'm going to call here Z, I'm going to call here Y. Now, please always consider our displacement from the center. We are going to consider our displacement as when we are moving from the center to what? To the right hand side or to the what? To the left hand side. And displacement now, because we are moving to the right hand side or left hand side, that's in the horizontal direction. Meaning our displacement is going to be expressed as what? As x. So if you displace your bulb from the center and it is now at what? At z, it means you have maximum what? Displacement, which is going to be equal to what? Equal to a. Now z is on the circumference of the circle, right? Isn't it? Now hope you know that if I'm to rotate this particle now, let me call this particle P. This bulb now, this particle P. If I'm to rotate it along this circle now, you know, and the length from the center is always going to be what? Going to be equal to what? To the radius of the circle, isn't it? If it is here, it is still what? A, but I can't call this one x anyway, but it's A, right? Here is P now. From here to here is A, which is equal to the radius of the what? Of the circle. Hope you know that x for here, x is equal to r, and it's also equal to what? To A. Displacement is equal to the radius, and then which is now also equal to what? To A. And don't forget that r or A is used to represent the what? The amplitude of oscillation, which is the maximum displacement. So meaning here we also have maximum what? Displacement. But here now, if you check from here to here, this particle has been turned from here to here. This particle has been turned through an angle what? Angle theta. Please watch. Let me shift this thing up a bit. Let me shift it up a bit. Okay. So this particle P here. Okay. So this angle theta. But this time around, at this point P, please watch. At point P, if you are to draw down vertically. Now, I said we want to consider our displacement. How? Horizontally. We are considering our displacement horizontally. Now, who can tell us the horizontal displacement now from the center here is from where? From here to what? To here, isn't it? Now, is this one up to amplitude now? It's no longer up to the what? To the amplitude. So we call this one what? X. Just call it x. But here we can't say x is equal to what? To r or a. From here to here is ordinary x displacement. But from here to here is what? Is our a or the what? The amplitude. Now who can tell us what is the relationship between x, our displacement, and what? And a. What is the relationship? X is adjacent. A is what? Hypotenuse. This is a vertical line, so here is 90 degrees. So that cos theta is going to be equal to what? X over what? Over A. This is the hypotenuse, this is the adjacent. Here is the opposite. And then if you make x the solid formula, x is going to be equal to what? A cos what? Cos theta. A cos theta. Now, if you do not forget our formula, let's call this one equation 1. If you don't forget our formula, omega is equal to theta over what? Over t. And theta is equal to omega what? T. So let's substitute this formula into this equation. So that x will now be equal to A cos what now? Omega t. Since theta is equal to what? Omega t. Let me call this one equation what? Equation 2. I'll call this one equation 2. Now, what am I trying to derive? This equation. That is what I'm trying to derive. Now, for you to be able to arrive here, you must be conversant with differentiation in your mathematics or further mathematics. Differentiation, especially how to differentiate trigonometric function. So x is our displacement. Don't forget, x is our what? Displacement from the equilibrium position. A is our what? Amplitude. Omega is our what? Angular speed. T is our what? Time. Now we are going to differentiate x now with respect to what? To t. You know, if you have y equals to 2x squared, for example, they will ask you to differentiate y with respect to what? To x. But here now, t is now a function of what? Of x. Here, here, y is a function of what? Of x. Yes, here, x is a function of what? Of t. So we are going to be differentiating x with respect to t. And don't forget, imagine if I have something like this, y is equal to 2 sine theta. Don't forget, let me just use sine theta. Differentiate sine theta, what do you have? The y the theta is what? Is what? Cos what? Cos theta. Y, if I differentiate cos theta, the y, the theta will be what? Minus sine theta. So you must be conversant with these standard derivatives. But if you now have y is equal to sine 2 theta, please, I don't want to toss, this is not what I've come to teach. I don't want us to take us through this rigor. You know, the y the theta is going to be equal to what? These two will come out, right? It will come out. We have what? 2 what? Cos what now? 2 what? 2 theta. Almost the same thing. But what is multiplying theta has to come out and come behind. There's an explanation for that. Function of a function. While if it is y equals to cos 2 theta and you have to differentiate this, what do you have? You're going to have y equals to, since when you differentiate cos, you are going to have minus what? Minus sine. This is going to be minus 2 sine what? Sine 2 theta. This is still going to be repeated. Okay? So we are going to apply that knowledge here now. You apply that knowledge here. So you can write this on somewhere. You can write this somewhere. So let's apply that knowledge here. Differentiate x with respect to what? To t. Meaning this omega now is the one standing as our what? As our 2 from that y equals cos 2 theta. Yes. Now, but this one is just a constant. It's a constant. So it's just going to multiply whatever we differentiate here. So it means the x now. This is going to be the x, the what? The what? The t. This one is just a constant. So the x, the t will now be equal to, what will come out now? Omega. Then when you differentiate cos, what do you get? We get minus what? Sine. So this minus omega times there was a here before, times a, then what do you have again? Sine omega t. So that the x, the t will now be equal to minus omega a sine omega t. But since x is displacement and t is time, this means this is changing with displacement over what? Changing what? In time. And according to your definitions of times in motion, what is changing displacement over changing time? That's what? Velocity. So it means our velocity, v now, is equal to minus omega a sine what? Omega t. V equals to minus omega a sine omega t. Alright? Then square both sides. Do what? Square both sides. So let's square both sides. What do you have if you square both sides? V square will now be equal to minus omega a sine omega t, everything square. So v square will now be equal to, when you square minus, it turns to plus, right? So this one goes. Then this omega square, right? Are you following? Then a what? A square. Then what happens here? Sine what? Sine square, right? Omega t. Sine square omega t. Are you following? Now, if you express this, if only this one is our theta, do you guys remember that sine square theta equals to 1 minus cos square theta from your trig identity? sine square theta equals 1 minus cos square theta. So that's what we're going to do here now. So yeah, let's go. V square equals omega square a square into what now? 1 minus what? Cos square. Now the whole of this now, omega t is representing our angle, our theta. So cos square omega what? Omega t. Okay. Now can we open bracket? Can we open bracket? So let's open bracket. V square will now be equal to omega square a minus omega square a square minus omega square a square cos square omega t. Okay? And then V square will now be equal to, I'm going somewhere, please. Factorize only omega. Only omega. I will have what? Omega square into a square minus what? A square cos square omega t. Now let's come here. Let's come back here. You remember this? Okay. X. Oh yeah. Please let's square both sides of the equation here. What do we have? S square equals a square cos square what? Omega t. Now let's substitute this equation. Carry the whole of this equation. Compared to what we have here. What do we have here? A square cos square omega t. So what is our a square cos square omega t? That's what? X square. So we now have v square equals omega square into a square minus, now the whole of this becomes what? X square. So we can now find the square root of both sides. This is what we are going to find the square root of both sides. So this is going to be square root of v square equals square root of omega square into a square minus what? X square. Then this cut this. We have v equals to, then this is going to be square root of what? Omega square times square root of a square minus x square. Did you remember your surd expression? Root a times b is equal to root what? A times what? Root b. So these are a and these are what? B. Omega is our a, and the expression we have in the bracket is our b. So that v will now be equal to this square root. Also we take care of this. So we have root, so our omega mean, then root a square minus x square. So what is the meaning of this formula? This formula now is the formula we use to calculate the speed. The formula we use to calculate speed for displacement at any point in time, whether you have amplitude or minimum displacement, which is zero displacement, or you have, or your anywhere your object is your body that is undergoing simple harmonic motion. Anywhere it is, anywhere you have displacement, you can use this formula to calculate the speed at any instant what? Instant time. At any what? Instant time. Now, I'm going to explain the implication of this formula, because this formula can also lead to V equals to omega what? Omega A. And who can tell us the condition upon which the formula will lead to V equals to omega A? Who can tell us the condition? Who can tell us? That is when our displacement is equal to what? 0. When displacement is equal to 0. Just watch. We are going to have V equals to omega root A square minus what? Minus 0 what? 0 square, and V will be equal to omega root only A square. So V will be equal to omega what? A. Because this will cancel this. Then let me tell you the implication of this formula, and then I'm going to give you an example to buttress my point. Now look at this. This is my pendulum bob once again. This is the center, the equilibrium position, which is C. You displace it to this point, then it swings to this point, also this point A, and this point B. This is the path of the motion of the object. Okay? So, if I'm to explain the energy of this motion and then the speed, you're going to have maximum PE here and here, point A and B. Then zero what? Velocity. There's zero velocity here, but maximum what? Maximum what? Maximum potential energy. Zero kinetic energy. I think there was something I even forgot to give to you from this equation. I was also supposed to show you that acceleration, linear acceleration A equals to minus omega square what? Square A, or omega square x. I was supposed to show you that. To show that acceleration equals to minus omega square A. I think we can continue that from here. Can we? Yeah, let's continue from here. Because we are going to need it. Because here, at point A, acceleration is what? Is maximum. Because acceleration depends on what? Displacement. So when we have maximum displacement, acceleration is going to be what? Maximum. Imagine if there's no acceleration, if there's no amplitude at all, there's no displacement at all. If this one is equal to 0, maybe x, when x is equal to 0, what will happen to acceleration? 0. So at the center here, acceleration is what? 0, when there's no displacement. But when we have maximum displacement, acceleration becomes what? Maximum. Meaning acceleration reduces as you go here, as you go towards the center. And as you move away from the center, acceleration is going to what? To increase as our displacement increases. And the acceleration becomes maximum when we have maximum what? Displacement. So let us see how acceleration is equal to minus omega square x. From the beginning, I wrote this. I said A is proportional to what? To minus x. And then A will now be equal to minus omega square x. It means this is standing as our what? Our constant of proportionality. So let's check. So let's continue our derivation from here. This is V, right? V equals to minus omega A sine what? Omega t. And what is acceleration? Change in velocity over change in what? In time. So let's differentiate this. Meaning we are going to do dv, the what? dt. And dv dt will now be equal to minus omega A times. Now this one will come out, right? Times what? Omega, then times what again? When you differentiate sine, you now have what? Cos what? Omega t. So this is going to be omega times omega. Minus omega square A cos what? Omega t. So this is dv dt. And what is dv dt? That's acceleration. Minus omega square A cos what? Omega t. Don't forget again. What is A cos omega t from the beginning? That's what? X. That's what? X. Isn't it? You remember? So A will now be equal to minus omega square x. So this how we have our acceleration equal to minus omega square x. But where am I going to? Where am I going to? Here. At point A, velocity is equal to what? Is equal to 0. This is it. When I displace it, I have not released it. This is where I have maximum what? Displacement. So 0 what? Velocity. But the moment I release it, just at the point of release, acceleration will be what? Maximum. As it's going towards the center, acceleration is what? Is reducing. Because acceleration depends on x. So then when it gets there, this way is going to have maximum what? Maximum speed. So even if it's for you to cram this expression, this convention that at the maximum displacement, acceleration is what? Maximum. Y velocity is what? Is 0. At the center, acceleration is what? 0. It's the reverse. Y velocity is what? Is maximum at the center. Velocity is maximum at the center. Here too the same thing. Here is also maximum displacement. Acceleration is what? Acceleration here is maximum. While the velocity or speed, we use both velocity and speed interchangeably, is what? Is 0. While when you come back here again, velocity is what? Or speed is maximum. Why? Acceleration is what? Is 0. Okay, so you are going to see from this formula. So please take note of this point. At the extreme ends, at the extreme ends, acceleration A is what? Is maximum. Maximum. That is A equals to minus omega square A. Where this time around x is going to be equal to what? To A. While at the center, acceleration is what? Is what? 0. Why? If you use this formula, this A is displacement, right? At the center, is there any displacement? Can you see? Here, there's no what? No displacement. Here now, there's no displacement. So our x, or normally this formula is supposed to be A equals to minus omega square what? Square x. But at the extreme end, x will now become what? A. Please don't forget, x will become A. Because x is now, it has become maximum displacement. So meaning at the center now, since there's no displacement, there's no horizontal displacement, it is at the center. So what happens? Acceleration becomes what? 0. Since x is what? 0. A will now become 0. No matter what your omega is, A becomes 0 at the center. Then for velocity, at the extreme end, velocity equals what? 0. Because, please, what I want to do now is very important because x is now what? Is now A. Now, let me show you from that formula. Since V is equal to omega root what? A square minus S square. V will now be equal to omega root A square. So, at the extreme end, x is equal to what? A. Our displacement x, our horizontal displacement x is now equal to the maximum displacement what? A, which is the amplitude. We now have maximum displacement. So we now there's amplitude here before. So since x has now become A, what will happen? Substitute now, we now have what? A square minus A square. Therefore, V will now be equal to omega root what? 0. And V will now be equal to omega times what? 0. V becomes what? 0. You can see that even from this formula now, you can tell us what will happen. At the extreme end, speed equals what? 0. But at the center, who can tell us what will happen to speed? Is it going to be 0 or maximum? Okay. So at the center of oscillation, speed V is what? Is maximum. That's where we have maximum speed. Maximum speed. So from my formula, V equals to omega root A square minus S square. So at the center, what is our displacement? Displacement x is equal to what? 0. There's no displacement, horizontal displacement at the center. So if I substitute that 0 here, we have V equals to omega root what? A square minus 0 square, and V will now be equal to root A square only. V is equal to omega times what? This cancels out, we have A. And then V equals to what? Omega A. It means this formula is even used to calculate maximum what? Maximum speed. You can see how this formula now turned to this. It's been simplified to this. Okay? So I will give one more example. In my next video, I'm going to drop the energy of simple harmonic motion. Energy of simple harmonic motion in my next video. Example. Okay, this is the question on the board. A body was displaced 1.0 centimeter from the equilibrium position and allowed to undergo simple harmonic motion. Full stop. Given that the angular speed is 2 radians per second, full stop. Calculate 1. The acceleration at the extreme ends, comma, at the center and at 8 centimeter from the center. Okay. Solution. I think, let me use a simple pendulum for that. This equilibrium position, then you displace it to point A, then it oscillates through about C and then comes to point B. So this is what we have. Now, meaning my horizontal displacement from here to here is what? 1.0 centimeters. That's from here to here. From the center to this place, 1.0 centimeter. Okay? In fact, I should have given a question that says calculate the maximum acceleration. Okay. Now, who can tell us what are we going to do? Let's interpret what we have first. We have angular what? Speed, which is omega, isn't it? 2 radians per second. Now, who can tell us what this 1 centimeter represents? A body was displaced what? 1.0 from the equilibrium position and released, isn't it? So we displace this 1.0 centimeter. So what does that 1.0 centimeter stand for? What do you say? Displacement, right? X. So what kind of displacement? What do you say? Maximum displacement. Thank you. So our X is equal to what now? A. This displacement is not an ordinary displacement. That's our maximum displacement. But it is centimeter. So please convert to meter. So 1.0 centimeter divided by what now? By 100. That's going to be equal to 0.01, right? Meter. So that's our amplitude. Please don't forget. Now the question is calculate the acceleration at the extreme ends. And at the extreme end, that's why we say acceleration is what? Is maximum. When they say extreme ends, that's at A and B. It's going to be the same thing. So what's our acceleration? So acceleration at extreme ends, A equals to minus omega square what? A. Instead of using x, omega square x, we are going to use omega square what? A. Now please, we can ignore this negative sign. So this is going to be omega square. What's our omega? That's 2. 2 square, right? Omega square, that's 2 square times A. What's our A? 0.01. So that's acceleration equals to 4 times 0.01, and that's 0.0 what? 0.04 meter per second square. Meter per second square. Okay. Now, acceleration at the what? At the center. You should have even memorized that conversion I gave to you. That acceleration at center is what? 0. But without even telling us that it is 0, without memorizing, if you use formula at center, what's our displacement? Because acceleration depends on what? On displacement. Our x equals what? 0, isn't it? So A will now be equal to minus 2 square times 0, and A equals what? 0. 0 meter per second square. So at the center, acceleration is 0. Then the next one says acceleration at 8 centimeter from the center. You know, if here to here is 1 centimeter, around here should be 8 what? 8 centimeter, right? Which is now equal to 0. Yes, 8 centimeter from the center. I think I just made a mistake, sorry. I just made a mistake. Thank God for that mistake. Thank God for that mistake. It is not possible for you to have a displacement, a displacement more than your what? Your amplitude. So this is supposed to be 0.8. That's a big mistake. That's 0.8 centimeter. So this can never be more than your displacement, your maximum displacement when you have to release it. So here is now 0.8, not 8. So this is going to be 0.008 meter, isn't it? Okay. So what's our acceleration there? So at 0.8 centimeter from the center, A will now be equal to minus omega square what? X, and A will be equal to 2 square times, you can ignore the minus I told you, that's 0.008. So that's equal to what? 4 times 0.008. What do you have? 0.032 meter per second square. So you know, I told you that acceleration decreases as we move towards where? The center. So you can see that this one now is more than this. 0.04. More than this now. Then at the center, what happens? At the center, what happens? A is what? 0. So here, maximum acceleration 0.04. Here, what do you have? 0.032. Acceleration is decreasing. While at the center, what do you have? A equals to what? 0. So this is where we have maximum acceleration. You can see the proof from the question. So the purpose of this question is just to explain all I've been saying since. Okay? Now, we move to speed. How the speed fluctuates at every point along the path of the motion. The speed. That's number 2 now. The speed at the extreme ends. So this formula is always useful. V equals omega root a squared minus what? S squared. It's always useful. There are times that this formula cannot be useful. V equals omega what? A. This is only useful at the what? At the center. So yes, center and at the extreme ends. But at every other point apart from center or at the extreme end, you can't use this because some make mistake of using this one. You must, when they say at a particular distance, when you are given a distance for the center like 0.8 centimeter and you have to find speed, you can't use this now. Because this is no longer A, this is X. So this one comes in. So you use here now, you now use both what? For this, you use both A and what? And X. I know you don't understand what I'm saying. Okay. V will now be equal to what? At the what? Extreme ends. So at extreme end now, what is the value of X? Please always look for the value of your X. X first. Your X first. Not even A, your X. We already know our A. So what is X? X is what? At the extreme end. What is X? Oh, we've forgotten. X is equal to A, which is our maximum what? Displacement. This is at the extreme end now. X is equal to what? To A. So V will now be equal to what? Omega. Right? Root what? A squared minus what? A squared. Substitute since X is equal to A. V will now be equal to what? Omega root what? A squared minus A squared 0. And V equals to omega times what? 0. V equals to what? I've told you at the extreme end, what is speed? Speed is what? 0. So at the extreme ends, V is 0, V is 0. That's why I say this formula now. This formula V equals to omega A. It's only useful, I think, at the center, not even at the extreme end, because okay. A, we can, since this one is A now, it should be somehow treacherous to say A is equal to 0, because A is never 0. But if you say V equals to omega x, but I don't think formula like this exists. So we can now put x is equal to what? 0, but A can never be 0. Okay? But instead of calculating, just tell them, in case you have a question like this, just say V equals what? 0 at the extreme end. Without even calculating. So it's a convention that you can write out. Then the next one says at the what? Center of oscillation, right? So at the center now, what is V? Now what is X first? Always get your X. What is X? Has it been displaced at all at center? So it means X is what? 0 centimeter. Which is also 0 point, that's, sorry, I said 0 point. 0 what? 0 meter. In meter, you have to express the meter. So that V will now be equal to omega root what? A square minus what? S square. So V will now be equal to, what's omega? 2 root, what's A? 0 point what? 1 square. Then minus X is what? 0 displacement. So V will now be equal to 2 root 0.1 square. V equals to 2 times 0 point what? 1. V equals to 0 point what? 2 meter per second. So it's at the center that this formula is applicable. V equals omega what? A, or V equals to omega R. Because at the center, S is 0. So meaning this formula now is already reduced to what? To V equals omega A. So you can just use this formula straightly at the center. This formula is the one you're already slotting. Put your amplitude straight and your angular speed multiply. That's your speed. But the last one, this one must be applied now, where our displacement x is equal to 0.8 centimeter. So at displacement x equals to 0.8 centimeter, which is also equal to 0.000, right? 0.008 meter. What's going to be speed? Speed V equals to omega root A square minus S square. So you can see how useful this formula is. Very important formula. V will now be equal to, what is our omega? 2 root 0.1 square minus 0.008 square. And V equal to 2 root 0.1 square. That's 0.001. Then 0.008 square. 0.00064. So V will be equal to 2 root. If you subtract this, what do we have? You subtract it, what do you have?
0.000936.
V equals 2 times square root of this. 0.0612. Just 1 0 here.
Yeah.
So V equal to F multiply, what do we have?
No, I've already multiplied it.
You multiplied everything?
Yes.
Okay. So V is equal to 0.0612 meter per second. So you can see that V is in fact very small compared to the speed at the center, which is the maximum speed. You know, do you remember the diagram I drew? This is it, this is it, and this is it. So that here is C, A, and B. Don't forget that here is what? 0.1 meter. Then here, C very far to the center. Yes, 0.08. No, 0.008, right? Meter. No, sorry, this one is 0.01 meter, right? Okay, so that's it. So that as you are moving now, you know, here now, V is what? 0.2. Here, V is what? 0.0. Sorry. Here, V is what? 0. Yes, 0. What? 0.0612. Here, it is maximum. It is what? 0.2. So, at the center, is at here is small. Here is what? 0. The same thing will happen around here too. 0 here, small here, bigger here, maximum here. Right? Then again, it's not what? It will be decreasing again. 0. Now as you're coming down again, it will be what? Increasing. It will be maximum here. Now as you are going here again, it will be what? Reducing. Until it becomes what? 0. It's just like projectile. That where something is going up, speed is what? Is decreasing. Until it becomes what? 0 at maximum height. So please, this is the end of today's class. Like, comment, subscribe, and share to your friends so that they can benefit from this channel. Thank you. God bless.